Alright, what is halfway between the number 10 and the number 16,000? Arithmetically, you would add them up and average them and get 18,005. But that's not what we mean in logarithms. So a big step, moving from the middle school to the high school in many ways, is learning to start thinking multiplicatively. What's halfway between x to the second and x to the eighth? You wouldn't add them up and divide by 2, you would add up their exponents and divide by 2 and say x to the fifth is halfway between them. And that's basically the idea with logarithms, to think about distances multiplicatively. So how would this be done? Well, to go from 10 to 16,000 doesn't mean adding 15,990, it means multiplying by 1600. So what's halfway to multiplying by 1,600? You could multiply by 40, and then multiply by 40 again. If you multiply 10 times 40 times 40, you get to 16,000. So halfway to 16,000 would be 10 times 40, 400. 400 is sometimes called the geometric mean of 10 and 1600. It's halfway there multiplying. And thinking of everything multiplyingly is what logarithms are doing. They basically follow the opposite of the rules of exponents, but we'll get to that in a bit. This statement is, I think this is log base 3 of 81. That's how it's said. Here's what it means. The number of 3's in 81. So how many 3's are there in 81? 1, 2, 3, and this is 27, 4. There are 4 3's in 81, multiplicatively. So the answer to this, the way to simplify this would be the answer 4. Let me ask you a more complicated question, or present you with a more complicated challenge. How many 4's are there in the number 32? Well, here's a single 4 it takes to make 4. It takes 2 4's to make 16, and it takes 3 4's to make 64. So the number of 4's in 32 is somewhere between 2 and 3. Is it exactly 2.5? In this case, yes. Because multiplicatively, if you broke that 4 up into 2 2's and cut just half of that, that's exactly 2.5 4's in the number 32. How about in an uglier number? How about log base 4 of 30? Well, we're not there yet, it's more than 1. We're not there yet, it's more than 2. It's less than 3. It's a little bit less than 3.5. It's some decimal, 2.4 something something something. I don't know exactly, and you don't have to. But the point is to understand how logarithms work. Logarithms follow different rules from the rules we follow. Let me present you with this. You know what? I don't like 3's. Let's do this. This will illustrate it better. The number of 2's in 4 plus the number of 2's in 8 is equal to the number of 2's in 32. How do I know that? Well, How many 2's are there in 4? 2. How many 2's are there in 8? 3. Remember, we need to think multiplicatively. 2 times 2 times 2 makes 8, so there are 3 2's in 8. And how many 2's are there in 32? 2 times 2 times 2 times 2 times 2. So this statement is true. What that means is, in short, when you have different logs with the same base, so the number of 2's in 4, the number of 2's in 8, and they're being added together, you can multiply the numbers. That means that you can do this. Oops, I can't write. I have 10's on the brain. This problem is solvable. How many 10's are there in 4? I don't know. Less than 1. There's not even a single 10 in 4. How many 10's are there in 25? I don't know. More than 1, but definitely less than 2, because 2 10's makes 100. How many 10's are there in those two things combined? Well, there are 2 10's altogether in those combined. This is less than a single 10. It's probably like 0.6. And this is more than a 10, but way less than 2, probably about 1.4. And you add them together, you will end up with 2. Because you can combine them multiplicatively. The number of 10's in 4 plus the number of 10's in 25 is the same as the number of 10's in 100, which is there are 2 10's in 100. You'll notice that this follows the opposite of the rules of exponents. In the rules of exponents, when you multiply, you actually add the exponents. Logarithms are the opposite process, and so when you see addition, you multiply. And just like you can only do this when x is the same as x, you can only do this when 10 is the same as 10. So that's how to think of logs. Let's see if we can find a good example here. Here we go. Compute. Right. So using the rules of logs, I can combine these and say the number of 2's in 16 plus the number of 2's in 10 is the number of 2's in 160. I don't know how many 2's there are in 20, but if I subtract the number of 2's from in 20 from the number of 2's in 160, that is going to be the number of 2's in. Now what's the opposite? Addition you multiply, so subtraction you divide. Divide them, you get 8. And in many ways this is all about factoring, right? This is 2 times 5, and this is 2 times 2 times 5. So when you take the number of 2's in this and remove the number of 2's in that, this had a single more 2 than this did in its build. And so that means you would end up with a single to a negative 1, negative 2. You would end up removing 1 more 2 than you added. You know, you start with this, you add a certain number of 2's, you subtract a certain number of 2's, but you end up subtracting 1 more 2 than you added. So if you subtract a single 2 altogether from 16, you're going to end up at 8, multiplicatively. How many 2's are there in 8? There are 3 2's in 8. 2 times 2 times 2. The answer to that is 3. And it's a pretty straightforward question. Alright, I want to do one example from exponents, because there's also a question on exponents in here that we should look at. What did I say, 2014, number 3. Okay. they say the solutions to this equation are a number a and a different number b minus log base 2 of c. And they say, figure out what a times b times c is. All right, let me show you an approach here. First of all, I'm going to move everything to the same side. This is a quadratic, hiding, pretending to be something else. Already looks quadratic-ish. Now, 2 to the x plus 1 is the same as 2 times 2 to the x. The reason for that is because there's one more 2 in this than there would be in 2 to the x. So I'm going to split that 2 out, and then I'm going to rewrite this as that. And I'm going to do something that you're going to see fairly often. I'm going to substitute in something more simple for something more complicated. I will declare that since 2 to the x is really messing up my view of this, I'll declare 2 to the x to be the same as y, which I've just invented. That means I can remove 2 to the x and replace it with y. And I could remove 2 to the x and replace it with y, but I'm going to use one of the rules of exponents first. 2 to the 2x is the same as 2 to the x squared. I know this because of the rules of exponents, which you learned in Algebra 1, I think, or Math Exploration, or whatever. You would multiply those exponents and get 2x, right? So I'm going to replace this first with this, and then, since 2 to the x is y, with this. Why am I doing this? You'll see. Give me 1 second. This then becomes I'm just going to rewrite it up here from down there. This mess then becomes this much simpler quadratic equation which we can solve for y. So here's what I do. I factor it to try to solve. The numbers multiply to a positive but add to a negative, so both of them are negative. Could it be 1 and 8? 1, no. Could it be 2 and 4? Yes. Yes, I'll put the 4 here and the 2 here. And that works out. Okay. So that means that y equals 4, or y equals 2/3. Y equals 4, great. Y equals 4, or y equals 2/3. All right, 2 to the x equals 4. What could x be? 2 to the what is 4? 2. So x could be equal to 2. 2 to the x equals 2/3. So what could x be? So the question is, how many 2's are there in 2/3? And that's why you see logarithms here. How many 2's are there in 2/3? We're looking for the number, I can't write G is the right size, the number of 2's in 2/3. And that is the same as the number of 2's in 2 minus the number of 2's in 3. Because when you have division, you can split it up, and in subtraction, the opposite of rules of exponents. The number of 2's in 2 is 1. And that's what they mean by this over here. One of the solutions, we figured out was 2. The other solution was 1 minus log base 2 of 3. And then they ask, what is compute A times B times C? A was 2, B was 1, C was 3. 1 times 2 times 3 is 6. The answer they want is 6. That's a level 3 challenge problem, and you'll see a lot of those sorts of things again and again. Situations where you have to take 3 times 2 to the 2x and like 4 times, well, 2 to the x plus 3, and realize that you can transform this into a quadratic by replacing this with 2 to the x squared, and then substituting this for like squiggle. I called it y, but whatever. And then realizing that over here, you can split 2 to the third off from 2 to the x, and 2 to the x becomes whatever, and that becomes 8, I called it y, plus 3y squared, and then, oh look, I've got a quadratic equation I can solve. So this is the sort of nonsense they pull on us. Thank you very much. They do that to us. Yeah, have fun with the problems. Feel free, if you find a clever solution or want to show a video of yourself solving this problem, to post your own videos and link it in the comments so that people can see how you solve various problems. Of course, I have the answer packets also.